Hello and welcome. This is another functional group packed video dealing with carboxylic acids and no less than 5 of their derivatives. We'll deal with carboxylic acids themselves and also esters, acyl chlorides, acid anhydrides, amides and nitriles. We'll only deal with one new type of mechanism, although I'll show you quite a few variations of it, and we'll also discuss the concept of resonance, a purely imaginary but extremely useful way of representing the delocalization of electrons. You'll remember this from last semester, I've just copied this from one of my previous videos, that carboxylic acids can readily lose a proton to form this carboxylate anion. Alcohols can technically do this too, but they're much less happy to do so because the negative charge on the carboxylate anion can be delocalized between the two oxygen atoms, whereas it's held on a single oxygen atom in the alkoxide anion. We can represent this delocalization using curly arrows. If you start from this structure, then you can see that if we move these electrons into this bond and push electrons out of this double bond onto this oxygen, then we get this structure. To get back again, we perform the reverse process. We represent the interconversion of these two structures with a double-headed or resonance arrow. Resonance is a purely imaginary process, as I said, because neither of these two structures actually exists. The carboxylic acid really exists as this sort of structure, with 1/2 of a negative charge on each oxygen. However, we use the concept of resonance to allow us to draw these simple structures while still acknowledging that delocalization takes place. Resonance can partly be used to explain the reactivity of the different carboxylic acid derivatives. Here are the main 5, acyl chlorides, acid anhydrides, esters, carboxylic acids themselves, and amides, and I've put them in order from the most to the least reactive. And this is in part due to delocalization effects. In acyl chlorides, delocalization is poor because chlorine is large and it's quite electronegative, so it doesn't give up its electron density. But all the others have alternative resonance forms. If we push electrons from this atom here up onto the oxygens at the top. In an acid anhydride though, there are 3 oxygen atoms fighting over the electron density, so delocalization is not great. In esters and carboxylic acids, 2 oxygens are fighting over it, so the situation is better than in acid anhydrides, and so these molecules are more delocalized and hence more stable and less reactive. In an amide though, the oxygen can more easily pull electron density away from the less electronegative nitrogen, so the delocalization is more extensive and the molecule is even more stable. Another factor to consider is the leaving group. In the absence of an acid catalyst, if we substitute at this carbon, here, here or here, then these are the leaving groups. Chloride is a very stable anion and so a very good leaving group, while a carboxylate is not so stable and hence not quite so good. These two are really not good leaving groups at all, so an acid catalyst is highly desirable, while this is a completely rubbish leaving group and acid catalysis is essential. Okay, so now let's do the specific reactions of each group. Carboxylic acids are typically formed by oxidation of alcohols or aldehydes, although you'll see another method later in the course, and they have a range of useful reactions. Firstly, they can react with bases such as sodium hydroxide to form salts, and also with hydrogen carbonates and carbonates to form salts and carbon dioxide. These reactions are very useful tests for the presence of acids. If the solution fizzes, then this reaction is taking place and the CO2 is being given off. Probably the main group of useful reactions, though, is the various nucleophilic substitution reactions that carboxylic acids undergo. We'll only do the mechanism of ester formation, but we can also form acid anhydrides and acyl chlorides directly from carboxylic acids. You can see that these first 2 reactions are equilibria, so a method of forcing them over to the product side is needed to get good yields, whereas the final one where the carboxylic acid is reacted with thionyl chloride to form the acyl chloride, is irreversible because sulfur dioxide gas is released. Another useful, although experimentally tricky reaction, is reduction back to the equivalent alcohol. Unlike reduction of aldehydes and ketones, which uses NaBH4, carboxylic acids and their derivatives require use of the more powerful reducing agent lithium aluminium hydride. This is because the delocalization seen in carboxylic acids and their derivatives makes them more stable and so less reactive than aldehydes and ketones. Lithal can also reduce aldehydes and ketones, but it's a bit excessive in those cases. Finally, we can decarboxylate carboxylic acids by heating with very concentrated base, losing CO2 to form an alkane or other hydrocarbon with one fewer carbon atom than the carboxylic acid. We won't do mechanisms for anything on this slide, but you need to be aware of these reactions and the conditions to use. The only mechanism we'll consider here is the formation of esters. As carboxylic acids are not very reactive, an acid catalyst is required. The acid catalyst must be an electrophile, as it's positively charged, so the carboxylic acid must act as a nucleophile. This converts the carboxylic acid, which is a poor electrophile, into this charged species, which is a great electrophile. The alcohol can then come in, it will act as the nucleophile, attacking this carbon, causing electrons to flow up onto this oxygen. Now, proton transfer from this oxygen to this oxygen generates this species, and electrons can then flow back down from this oxygen to boot out water and generate this. If I draw this out differently, you can see that all that's left is for this proton to leave, electrons flow onto this oxygen, and we've formed our ester. You should go through each step here and make sure the curly arrows, the charge balance and the atom balance make sense to you in all cases. I'll now go through the reactions of the different carboxylic acid derivatives, starting with the most reactive, acyl chlorides. Basically, almost all reactions of carboxylic acid derivatives are nucleophilic substitutions with similar mechanisms to the esterification that we've just seen. We can make any of the less reactive derivatives by this method, and acyl chlorides are so reactive that no catalyst is required. If we use water as our nucleophile, then we get back to the carboxylic acid, whereas if we use another carboxylic acid, then we make an acid anhydride. Similarly, if we use an alcohol, then we can make an ester, and if we use an amine, then we make an amide. Acyl chlorides are therefore very versatile reagents. They are so reactive though that they don't tend to last very long, so we usually make them from the carboxylic acid immediately before we use them. Reactions with acyl chlorides are relatively simple mechanistically, as you don't need to worry about an acid catalyst. The acyl chloride is an electrophile, as this CO double bond is polar, and it can be attacked by a range of nucleophiles. I'll use an alcohol here, but the mechanism is straightforward to adapt to other nucleophiles. The nucleophile attacks this carbon, as you saw previously, pushing the electron density up to make this oxygen negatively charged. There's no need for any proton transfer now. Electrons can flow back down from this oxygen to boot out chloride. If I draw this species out differently, you can see again that this proton can leave to give the product. You can adapt this mechanism to hydrolysis or acid anhydride formation by changing what the R group is, or you can change it to amide formation by changing OR to NR2. The next derivative we'll consider is the acid anhydride. Again, we can make any of the more stable carboxylic acid derivatives, so although we can't make acyl chlorides, we can hydrolyze them back to the carboxylic acids, and we can make esters using alcohols. Again, we can make amides using the amines. The mechanism is essentially the same as with an acyl chloride. The nucleophile, again I'll use an alcohol here, attacks this carbon as before. Like with the acyl chloride, electrons can now flow back down to expel, this time a carboxylate anion, and then, let's draw that out differently again, deprotonation gives the product. You can adapt this mechanism to hydrolysis or amide formation, as I explained on slide 10. Although an acid catalyst is not completely necessary, we often use one in the lab to save time. In this case, the mechanism is similar to the ester formation I showed you on slide 7. The acid catalyst must be an electrophile, so now the acid anhydride must act as a nucleophile. That forms this species, increasing the electrophilicity and speeding up the reaction. The nucleophile can then come in as usual, generating this species, and now proton transfer from this oxygen to this oxygen generates this species. Electrons flow back down as before to generate this, expelling the carboxylic acid, and then I'll just show that OH bond. We get deprotonation to generate the product. Now, acyl chlorides and acid anhydrides are both relatively unstable, so we tend to make them only when we want to use them in a subsequent synthetic step. Esters, however, are stable enough to be stored for months at a time. We can, however, hydrolyze them back to the carboxylic acids, or we can react them with amines to make amides. The mechanism is very similar to the one for their formation. The ester is protonated by the acid catalyst, forming this species, and it's then attacked by water. Electrons flow up here, and then proton transfer sets everything up for the electrons to flow back down, kicking out an alcohol, and then this deprotonates to form the carboxylic acid product. Again, this mechanism can be adapted to amide formation by changing the nucleophile here. You should be able to see the strong similarity both to the mechanism for ester formation from carboxylic acids and to the mechanism for acid-catalyzed reactions of acid anhydrides. Amides, the next group we'll consider, are very unreactive, so we can't make many of the other derivatives, but we can still hydrolyze them back to the carboxylic acids, and in this case, we can use a primary amide to make a nitrile by eliminating water using phosphorus 5 oxide as a dehydrating agent. We won't do the mechanism for this one at all, and I won't go through the mechanism for hydrolysis here either, as it's essentially the same as acid hydrolysis of esters, except that an amine leaves instead of an alcohol. So now let's consider nitriles. So far, you've encountered two methods for making them, one in this video on the previous slide and one in the previous video. But another method is the straightforward nucleophilic substitution of a halogenoalkane, which I could have included in the previous video, but didn't. It's a straightforward mechanism, just like you saw in the previous video for the formation of alcohols from halogenoalkanes. Your nucleophilic anion simply attacks the back of this carbon, booting out the halogen to form the nitrile and the halide anion. Nitriles are also quite unreactive, but they do still have some useful reactivity. Again, we can hydrolyze them back to the carboxylic acid, this time losing ammonia, and we can reduce them to form amines, again using the strong reducing agent lithium aluminium hydride. Combining this reduction method with the formation of a nitrile from a halogenoalkane allows us to go from a halogenoalkane to an amine with one extra carbon atom in just 2 steps. We shan't do the mechanism of this, but I would like to consider this one now. The hydrolysis of a nitrile is the most complex mechanism you'll encounter here, although once again it is essentially a variation on the theme that you've already seen. Let's draw this nitrile out in full with the carbon-nitrogen triple bond showing. Nitriles, as I've said, are quite unreactive, so an acid catalyst is required, which is attacked by the nucleophilic nitrogen. That generates this electrophilic species, which can react with the nucleophilic water. Water attacks this carbon, pushing electrons onto the nitrogen and generating this species. To make the amide, though, we need a second water molecule to attack. In order to do this, first we need to transfer a proton from this oxygen to this nitrogen to generate this species, which again can be attacked by water. You should notice that this step is very similar to the second step over here. The water attacks the carbon, electrons flow out onto the nitrogen. And both steps are very similar to the reactions you've seen previously in this video, except that the electrons flow onto nitrogen here, whereas they flowed onto oxygens in earlier examples. Another proton transfer now sets this nitrogen up to leave, and the electrons flow down from this oxygen to boot out ammonia and generate this species, which you've seen several times over the course of this video. Draw it out differently, deprotonate it, and you have your carboxylic acid. And so we come to the end. We've discussed carboxylic acids and 5 of their derivatives in terms of their relative reactivity and their specific reactions, which are mostly based around nucleophilic substitution. I've shown you mechanisms for that both with and without acid catalysis. Several of these derivatives also undergo reduction reactions, although the mechanism of that is not required. I've also touched on the concept of resonance as a means of representing delocalization of electrons. In the next video, we'll take the concept of resonance a bit further by considering the reactions of aromatic compounds.